So here's something I only picked up recently. Typhoon names in the Western Pacific get recycled. There's a rotating list, and when a name comes back round, it just gets handed to whatever happens to be spinning out there that week. Bavi is one of those names. It's Vietnamese, it's a mountain, and it had already had a go. There was a Bavi back in 2020 that wandered north and hit the Korean peninsula. It was fine, in the sense that a storm can be fine. Nobody really talks about it. This year's Bavi is not that storm. What I want to do here is walk slowly through the entire life of one typhoon, from a smudge of cloud sitting over a place most people have never heard of, all the way to a tired rain band drifting across eastern China with nothing much left in it. There's no big reveal waiting at the end. It's just a storm, and storms are interesting enough on their own, without me dressing them up. Most of the bits here stand on their own, so if you drift off halfway through, you haven't missed a thing. And if you like this sort of stuff, subscribing helps. That's the whole pitch. Kwajalein is one of those place names that sounds slightly invented until you actually look it up. It's an atoll in the Marshall Islands, which is to say it's a ring of low coral islands sitting in the middle of an enormous stretch of open Pacific, wrapped around one of the biggest lagoons on the planet. The land itself is barely there. If you flew over it, you'd see a thin necklace of green and white sitting on blue, and you'd probably assume nothing much happens there, which is roughly correct most of the time. On the 25th of June, just east and slightly south of Kwajalein, there was a disturbance. That's the technical word, and I quite like it, because it's so beautifully non-committal. A disturbance isn't a storm. It isn't even a proper depression. It's a patch of the atmosphere that's slightly more interested in itself than the air around it. Clouds bunching up, thunderstorms firing off, dying, firing off again somewhere slightly to the left. Nothing you'd photograph. And that's how nearly every typhoon starts. That's the bit people skip. The conditions out there were good, and I'll get properly into what good means later on because it deserves its own section rather than a passing sentence. But the short version is that the water was warm, the air was wet, and nothing up high was blowing hard enough to knock the thing over. So the disturbance sat there and did what disturbances do when nobody's interfering, which is slowly get its act together. 4 days later, the Joint Typhoon Warning Center issued what's called a Tropical Cyclone Formation Alert. That's the first real institutional shrug in the direction of, right, this might become something. It's not a warning to the public, it's more like a note to the professionals. Keep an eye on this one. Then early on the 1st of July, the JTWC upgraded it to a tropical depression and gave it a number. 9th system of the season in the Western Pacific, W for West. That's it. That's the whole naming convention at that stage, and I find something quite funny about the fact that the most powerful storm to hit American soil in the whole record spent its first day and a half being called a 2-digit number and a letter. At midnight UTC on the 2nd of July, the Japan Meteorological Agency upgraded it again, this time to a tropical storm, and a tropical storm gets a name off the list, so 09W became Bavi. Now, here's the bit I actually want to talk about because it's the sort of thing that confuses people, and it really shouldn't. This storm ended up with 3 names. It's Bavi on the international list, which the JMA maintains for the whole basin. Its own introduction to the Joint Typhoon Warning Center, which is the American military forecasting body that tracks these things, and later on, when it got close to the Philippines, it picked up a 3rd name from PAGASA, the Philippine Weather Agency. They called it INDAE. 3 names, 1 storm. And every single time a big typhoon does this, you get people online treating it like some sort of shell game, like the names are being shuffled to hide something. I understand the instinct, I do, but it's the exact opposite of what's happening. 3 names means 3 separate organizations, answering to 3 different sets of people, all watching the same patch of sky at the same time, and all publishing what they see. That's not a cover-up. That's several independent bodies doing their jobs out in the open, and each using the filing system they've always used. PAGASA's system in particular is worth a minute, because it's a genuinely nice piece of design. They keep their own list of local names in Filipino for storms inside what's called the Philippine Area of Responsibility, a big box drawn on the map around the archipelago. The reasoning is simple and, I think, rather humane. If you're a fisherman in northern Samar, INDAE means something to you in a way OM9W never will. Warnings only work if people actually hear them, and people hear their own language. There's a small quirk with Bavi that made me smile. Pagasa gave it the name in day late on the 7th of July, even though the storm hadn't technically entered their area yet. It crossed the line at 3 a.m. Philippine time on the 8th, so for a few hours there, it had a Philippine name and no Philippine business having one. They just saw it coming and got the paperwork done early. Honestly, no notes. But back to the beginning of the thing, because I've skipped ahead. What I find genuinely difficult to get my head around is how unremarkable this all looked. Between the 25th of June and the 1st of July, if you'd been staring at satellite imagery of that patch of the Pacific, you would have seen almost nothing worth mentioning. A blob. A slightly better organised blob. A blob with a bit of a curl to it. 7 days of that. 7 days of a system doing absolutely nothing that would make you sit forward. And that's normal. Most of these things never go anywhere. The Western Pacific throws out disturbances constantly, the vast majority of which fall apart or drift into somewhere unhelpful, or just quietly give up. Forecasters spend a huge amount of their time watching blobs that never amount to anything, which is a job description I've thought about more than once, and always come away from with a lot of respect. The naming lists themselves are a bit of a joy, if you ever go looking. The Western Pacific list isn't like the Atlantic one, where it's all Andrew and Barbara and Charlie marching through the alphabet. The Pacific list is contributed to by countries all around the basin: Japan, China, Vietnam, Cambodia, the Koreas, Thailand, Malaysia, the Philippines, Micronesia, Laos, Hong Kong, Macau, the US, and each one submits names from its own language. So you end up with this genuinely lovely mix. Flowers, animals, constellations, mountains, like Bavi, words that mean storm cloud in one language, and someone's grandmother's name in another. It's one of the few international committees that produce something with actual character, and the list just cycles. Names come round again after a few years unless a storm is bad enough that a country asks for it to be taken off, which does happen, and which I'll come back to right at the end. The other thing about those early days that's worth sitting with is the distance. Kwajalein to Guam is well over 1,000 miles of open water. From where Bavi was born to where it made its name, there was nothing. No land, no islands to trip over, no cool water to run into. Just an enormous, uninterrupted, very warm expanse of ocean, and a storm walking west across the middle of it, with absolutely nothing in the way. That matters more than it sounds like it should. A lot of storms in a lot of basins get born too close to something. They form, they organise, and then within a day or two they've clipped an island or wandered over a cold patch or been shoved sideways by winds high up, and whatever they might have become never happens. Geography kills more storms than we tend to give it credit for. Bavi had a clean run. It came into existence in the emptiest part of the biggest ocean on Earth, pointed roughly west, and had days of nothing but road ahead of it. One more detail from this stretch that I think is quietly telling. When the JTWC put out that formation alert, the reasoning noted the disturbance had been gradually intensifying over favourable conditions. Gradually. That's the word they used, and at that point it was the right one. Bavi spent nearly a week being gradual. It did not stay gradual. But that's the next bit, and I'd rather not rush into it, because the 7 quiet days deserve to be their own thing. A storm's whole life gets remembered by about a day in the middle of it, and everything before that just becomes a footnote in the meteorological history section, which strikes me as slightly unfair. The week where nothing happened is the week it built everything it needed. It's just that nothing looks like nothing while it's happening. Anyway, let's talk about what happened when it stopped being gradual. 70 knots to 125 knots. 18 hours. That's the whole thing, really. That's the sentence that put Bavi in the record books, and it's worth just sitting with the numbers for a second before I explain what they mean, because the numbers on their own are quite something. At 6 in the evening UTC on the 2nd of July, the Joint Typhoon Warning Centre had Bavi's 1-minute sustained winds at 70 knots. That's a low-end typhoon. Respectable. Nothing you'd write home about in a basin that produces dozens of these things a year. By midday on the 3rd, 18 hours later, they had it at 125 knots. Category 4 equivalent. Same storm, same afternoon and evening and following morning. There's a formal term for this, and I have a small problem with it. The term is rapid intensification. The bar for earning that label is a gain of 35 miles per hour in wind speed over 24 hours. That's the official definition, and it was written to describe the exception rather than the rule. because most storms genuinely never do it. Most storms strengthen the way you'd expect anything to strengthen, in fits and starts, gaining a bit, losing a bit, wobbling along and generally taking their time about it. Bavi gained 75 miles per hour in 24 hours. Over 36 hours the gain was 100, so it didn't creep over the threshold, it more than doubled it and kept going, and my problem with rapid intensification is just that it's such an aggressively beige name for what is, physically, the most violent thing a tropical cyclone is capable of doing. It sounds like something that happens to a spreadsheet. It sounds like a phrase invented specifically to be read aloud in a calm voice at a briefing, which, to be fair, is probably exactly what happened, and there's a professional logic to it. Forecasters have to be the unbothered ones in the room, and you don't achieve that by naming things the terrifying bit. But still, the most dangerous behaviour in atmospheric science is called rapid intensification, and meanwhile a mildly annoying weather front over Britain gets called a bomb cyclone. Priorities. Anyway, what does it actually look like, this thing? The satellite imagery is the part that gets me. Because you can watch it happen, and it's genuinely eerie in a way that's hard to explain if you haven't seen a loop of it. A disorganised storm looks like a mess. That's not me being flippant, that's more or less the technical picture. The centre is broad and vague. The thunderstorms are scattered around it in clumps. There's no symmetry to it. If you asked 10 people to point at the middle, you'd get 10 answers and a bit of an argument. When rapid intensification kicks in, all of that goes away in a matter of hours. The thunderstorms pull inward and organise themselves into a ring. The ring tightens. The whole mass goes symmetrical, like something being spun on a potter's wheel. And then, in the middle of it, an eye opens. A clear, round, sharply defined hole punched right through the centre of the cloud. In Bavi's case, the eye emerged inside what forecasters call the central dense overcast, which is the big solid slab of high cloud that sits over the core, and it appeared quickly and it appeared well defined. The outflow, the air escaping from the top of the storm, which I'll come back to, expanded enormously in every direction at once. The cloud tops got colder, which sounds like a strange thing to care about until you realise that colder cloud tops mean the thunderstorms are punching higher into the atmosphere, which means they're stronger, all of that inside a single day. The mechanism underneath it is a feedback loop, and it's elegant enough that I think it's worth going through slowly, because once you see the shape of it you'll understand why these things are so hard to stop once they get going. A tropical cyclone is a heat engine. That's not a metaphor and it's not a teaching aid, it's a literal description of what the machine is doing. Warm ocean water evaporates. The water vapour rises into the storm. As it rises it cools, and as it cools it condenses back into liquid. That's the cloud you're looking at, and condensation releases heat. It has to, it's giving back exactly what the ocean put in when it evaporated the water in the first place. That released heat warms the core of the storm. A warm core is a low-pressure core because warm air is less dense and weighs less, so the pressure at the centre drops, and when the pressure at the centre drops, air from further out rushes in harder to fill the gap. The steeper the pressure difference, the faster the air has to move. Faster air over warm water means more evaporation. More evaporation means more vapour, more condensation, more heat, lower pressure, faster winds. Round and round. That's the loop. It's self-reinforcing, and once it's spinning properly there are only really two things that stop it: running out of warm water or running into land, neither of which was available anywhere near Bavi on the 2nd and 3rd of July. The reason forecasters care about the speed, and not just the final number, is nothing to do with physics. It's to do with clocks. Think about what a place actually needs in order to get through a serious storm. It needs time. Time to issue warnings, time to open shelters, time for people to board things up, buy what they need, work out whether they're staying or going, and then actually go. That entire chain, every link of it, runs on knowing in advance roughly what's coming and roughly how bad it'll be. Now picture a storm that's a moderate typhoon when people go to bed and a category 4 when they wake up. Every hour the storm spends exploding is an hour the forecast spends chasing it. And the gap between what people were told to expect and what actually turns up is where the danger lives. It's not really the wind that catches communities out. It's the difference between the wind they prepared for and the wind that arrived. That's the whole reason this behaviour gets so much attention from people whose job is keeping others alive. The final intensity is the weapon. The speed of getting there is what loads it. There's one more number from this stretch I keep coming back to, and it's smaller than the others, but it lands harder for me. At one point on the 3rd of July, Bavi went from 157 kilometers per hour to 194 kilometers per hour in 6 hours. 6 hours, that's a working morning. That's the length of time it takes to do basically nothing in particular, and in that window a storm gained more wind speed than a lot of tropical systems ever manage across their entire lives. And by 9 in the evening, UTC on the 3rd, the JTWC had upgraded Bavi to a super typhoon, Category 5 equivalent, 140 knots. From tropical storm to the top of the scale in a bit over a day. The Japan Meteorological Agency, working with its own conventions, had by then upgraded it to a very strong typhoon and then to a violent typhoon, which is their highest category and which I'd argue is a better bit of naming than anything the Anglophone agencies have come up with. Violent typhoon. That's a phrase that tells you what you're dealing with. I want to be careful not to make this sound like the storm was doing something impossible or unnatural, because it wasn't. Rapid intensification is rare, but it is not weird. It's a documented, understood, well-described behaviour that a minority of storms exhibit when the conditions line up. The physics didn't break. The loop just found nothing to slow it down. Which raises the obvious question of why nothing slowed it down, and the answer to that is sitting underneath the whole thing, about 100 metres down, in water that had absolutely no business being as warm as it was. But now, let's talk a little about that water, because it's the thing everything else here sits on top of. Put 2 pots of water on the hob, heat them both until the surface of each one is exactly the same temperature, identical. If you dipped a thermometer in the top centimetre of either, you'd get the same reading and you'd assume they were the same pot. They're not. In the first pot, only the very top layer is warm and everything underneath it is cold. In the second, the warmth goes all the way down to the bottom. Now drop an ice cube in each and give them a stir. The first pot collapses almost immediately. There was never much heat in it, just a thin warm skin sitting on top of cold water. And the moment you stir, the cold comes up and the warmth is gone. The second pot barely notices. You can stir it as long as you like. There's a deep reserve of heat down there, and the ice cube isn't going to make a dent in it. A typhoon is the stirring. That's the whole analogy, and it's the single most useful thing I know for understanding why some storms fizzle, and others do what Bavi did. Because a strong tropical cyclone is a violent mixer. Its winds churn the sea underneath it and drag water up from below constantly. If the warm layer is shallow, the storm pulls cold water up under itself within hours and effectively cuts off its own fuel supply. It breaks itself. It's a lovely bit of natural self-limitation, and it kills a great many promising storms. If the warm layer is deep, the break never engages. The storm churns and keeps finding warm water no matter how much it drags up, and there's nothing built into the system to slow it down. Bavi was over the second pot, so let's do the numbers, because they're the quiet centre of this entire story, and they're less dramatic than the wind speeds, but they explain them. The sea surface temperature under Bavi, east of Guam, was running between 29 and 30 degrees Celsius. In old money, roughly 84 to 86 Fahrenheit. That's bath water. That's water you'd get into without any of the theatrical wincing and gasping that a British person considers a legally required part of entering the sea. Now, on its own, a number like that means nothing to you, unless you know what it's being compared against. So here's the reference point. There's a rough threshold that scientists use for the minimum sea surface temperature needed to sustain a tropical cyclone at all, and it sits at about 26.5 degrees Celsius. Call it 80 Fahrenheit. Below that line, the engine starves. There isn't enough evaporation, there isn't enough heat, and storms struggle to organise or hold themselves together. 26.5 is the floor. It's the bare minimum. It's the level at which a storm can exist rather than the level at which a storm can thrive. Bavi was sitting over water 3 to 4 degrees above the floor. And here's the thing about those 3 or 4 degrees. In this context, they are not a small bonus. They're not a rounding error on any already warm ocean. Every fraction of a degree above that threshold is more evaporation, more vapour, more fuel, more energy available to the loop, and crucially, a higher ceiling on how strong the storm can theoretically become. 3 degrees over the minimum is the difference between a system that might scrape together a modest typhoon and a system that can go all the way to the top of the scale. But the surface temperature is only half the story, and it's the half that gets quoted. The measurement that actually mattered here is called ocean heat content, and it's exactly what it sounds like. The total amount of warmth stored not just in the skin of the sea, but down through the upper layers of it. It gets measured in kilojoules per square centimetre, which is one of those units that means nothing to anyone outside the field, so let me just give you the comparison rather than pretend the number is intuitive. Under Bavi, east of Guam, the ocean heat content was running over 110 kilojoules per square centimetre. Later on in its life, as it moved west, it found water where that figure was over 125. Anything over about 50 is generally considered supportive of intensification. Over 100 is a very deep tank. Over 125 is the kind of reading that makes people who look at this stuff for a living go quiet for a second. That's the second pot. That's a warm layer with real depth to it, and it's why the storm could stir the ocean as hard as it liked and never cool its own fuel. And you can actually infer this backwards, which I think is rather nice. The fact that Bavi intensified as fast and as far as it did is itself evidence that the warm layer beneath it wasn't shallow. A thin, warm skin would have braked the thing. It didn't get braked, it accelerated, so the heat ran deep, and we'd know that even if nobody had measured it, just from watching what the storm did. Now, since we're on the subject of the water, there's a bigger piece of geography worth mentioning here. There's a region scientists refer to as the Western Pacific Warm Pool. It's a stretch of the tropical Western Pacific that holds the warmest open ocean water anywhere on Earth. Not warm in a nice holiday sense, warm in a structural load-bearing sense, and crucially it holds that warmth not just at the surface, but through a thick layer of the upper ocean. This is the main reason the Western Pacific is the most prolific producer of intense tropical cyclones on the planet. It's not simply that the surface gets hot. Lots of places get a hot surface for a few weeks. It's that the warmth has depth, and depth is a foundation a storm can draw on without exhausting it. I find the distinction between surface warmth and deep warmth genuinely interesting for a reason that goes slightly beyond storms. Surface temperature is fast. A stretch of calm, sunny weather can warm the top of the ocean quite quickly, and a stretch of wind and cloud can cool it again just as fast. It's weather. It comes and goes on a timescale of days. Deep heat isn't like that. Warmth stored through a thick layer of the sea accumulates slowly, over months, over years. It doesn't respond to a good week. It reflects the longer-term energy budget of the ocean, the slow arithmetic of how much has gone in against how much has come out over a very long time. So the ocean's surface is the weather, and the ocean's depth is the memory. When a storm behaves in a way that reveals deep warmth underneath it, as Bavi did by refusing to be braked, it's telling you something about the accumulated state of the basin rather than about a lucky patch of sunshine last Tuesday. That's a genuinely different category of information, and it's the reason a single storm's behaviour can occasionally tell you something real about a whole ocean. One last thing here, because it's the bit that made me put my tea down when I first worked through it. The energy involved is not on a scale that human beings have any intuition for. A mature tropical cyclone releases heat energy, through condensation, through that loop we walk through, at a rate that dwarfs anything our species has built. The energy released by the condensation inside one large typhoon, every single day, is on the order of hundreds of times the total electricity generating capacity of the entire human race. Not hundreds of power stations, hundreds of times all of them, every day. Continuously for as long as the storm sits over warm water, just by existing. We have never built anything that produces power on that scale. We're not close, we're not in the same conversation, and the source of all of it is the heat sitting in the ocean, which is what that sea surface number represents when you strip the units off it. It isn't just a temperature, it's a fuel gauge for the most powerful weather events the planet is capable of producing. And under Bavi in the first week of July, that gauge was reading very close to full. Right. Let's go and look inside the thing, because the machinery at the middle of it did something genuinely odd. Here's a thing storms do that I still find slightly absurd, in the sense that if you designed it deliberately, nobody would believe you. A powerful typhoon will occasionally decide to demolish its own engine and build a new one while still running at full speed. It's called an eye wall replacement cycle, and Bavi went through at least one of them, and it's probably the strangest single behaviour in the whole of tropical meteorology. Let me set it up. The eye wall is the ring of intense thunderstorms wrapped around the eye. It's the business end. It's where the strongest winds on the planet live, and it's compact. In a really powerful storm, it can be a fairly tight ring, and the eye inside it might be 20 or 30 kilometres across. Bavi's eye was measured at roughly 33 kilometers in diameter at one point, which is to say you could drop a decent-sized city into the calm bit in the middle. What sometimes happens in a mature, very strong storm is that a second ring of thunderstorm starts to form further out, an outer eye wall forming a concentric circle around the inner one, and these two rings are now competing for the same inflowing air, the same moisture, the same fuel. The outer ring is bigger, so it has a wider net, and it gradually strangles the inner one. The inner eye wall starves, collapses, and dies. The outer eye wall contracts inward and takes over as the new eye wall. While all this is going on, the storm weakens. It has to. Its core is falling apart. The peak winds ease off, sometimes by quite a lot, over a matter of hours, and then, once the new larger eye wall has settled in and tightened up, it re-intensifies. Bavi did this on the 4th of July. It weakened slightly overnight as the cycle ran, and by the following day it had re-strengthened all the way back to Category 5 equivalent. But here's the part that actually matters, and it's the bit people miss when they see the wind speed dip and assume the news is good. A storm that comes out of an eye wall replacement cycle is usually bigger. The new eye wall is further out than the old one was, so the ring of destructive winds is now wider. The peak wind might come down a notch, but that peak wind is now being delivered across a much larger area. You've traded a little intensity for a lot of reach. Bavi came out the other side of it enormous, and I mean that in a documented official sense, because the Joint Typhoon Warning Centre actually reached for a word in one of its warnings that I don't think I've ever seen in a technical bulletin before. They wrote that Bavi remains a gargantuan typhoon, with a wind field size ranking in the top 3% of all Western Pacific typhoons of the past decade. Gargantuan. That's in the official product. That's the calm professional forecasting body, the one whose entire institutional personality is not raising its voice, going with gargantuan. I've read a fair few of these bulletins now, and the register is normally so flat you could use it to level a shelf. So when the flat register cracks and someone types gargantuan into a warning, that's an organisation telling you something in the only way its format allows. Top 3% of the last decade, in the basin that produces more and bigger typhoons than anywhere else on Earth. That's the size we're talking about. Now, the other thing about the core of this storm, and this is the one I think is genuinely remarkable rather than just impressive, there's a concept called maximum potential intensity. The idea is straightforward once you accept the heat engine framing from earlier. If a storm is converting ocean heat into wind, then for any given set of ocean and atmospheric conditions there's a theoretical ceiling, a maximum. The strongest a storm could possibly get if absolutely everything went perfectly, and nothing interfered at all. For the conditions Bavi was sitting in, the University of Wisconsin Sims put that ceiling at roughly 200 miles per hour, with a central pressure of about 885 millibars. At landfall on Rota, Bavi had a central pressure of 910 millibars. That is close. That is uncomfortably close to the theoretical maximum, and it is genuinely rare for any hurricane or typhoon anywhere to get near its own ceiling. It almost never happens, because everything has to be perfect at once. The ocean, the shear, the outflow, the internal structure, the timing. And the atmosphere is a complicated enough system that perfection basically doesn't occur. Storms are always losing a bit somewhere. There's always some inefficiency, some dry air getting entrained, some wind-up top nudging the column off true. Bavi found something very close to perfect and ran nearly all the way to the top of what the physics would allow. I keep turning that over. Not the strongest storm ever, which it wasn't. Something more specific and, to me, more interesting. A storm that got about as much out of its environment as an environment can give. And then there's the eye wall itself, which produced the detail from this whole event that I'd put in front of anyone who thinks weather is boring. After Bavi passed through the Northern Marianas, radar imagery from Guam showed the interior of the west eye wall with a scalloped appearance. Not a smooth circular wall. Scalloped, like the edge of a shell. That scalloping likely indicates mesovortices, tornado-scale circulations embedded inside the eye wall itself. Little spinning cells living inside the wall of the bigger spinning thing, vortices inside a vortex, which means that the strongest winds in a storm like this aren't uniform around the ring. They're concentrated in pockets, and those pockets are themselves rotating, and if one of them passes over you, then the wind you experience isn't the storm's headline number, it's the storm's headline number plus whatever the little one is doing on top. These were first definitively observed during a Hurricane Hunter flight into Hurricane Hugo in 1989. A flight that, by the account of one of the meteorologists on board, very nearly brought the aircraft down. I think about that a lot. Somebody had to fly into the middle of one of these to find out that the middle of one of these has smaller ones inside it, and the way they found out was that the plane nearly didn't come back. There's something quite humbling in the fact that we only worked out this particular piece of storm architecture by accidentally flying into it and surviving. While we're on the machinery, the outflow deserves its minute too, because it's the piece nobody thinks about and it's the reason the whole thing works. Every engine has to vent its exhaust or it chokes. For a Typhoon, the exhaust is the air escaping at the very top of the storm 10 or 12 kilometres up, spreading outward like a lid being pushed off. All that air rising through the eye wall has to go somewhere. If it can spread out and get away cleanly, the storm can keep pulling more air up from beneath. If the exhaust backs up, the whole thing stalls. Bavi's outflow during that explosive stretch expanded massively and improved in every quadrant at once. All 4 directions, clean venting, no back pressure, a chimney with a perfect draft, warm deep water underneath, nothing up high knocking it over, and a chimney drawing perfectly. That's 3 ingredients, all lined up simultaneously, over the most productive tropical basin on Earth. And what you get when that happens isn't luck and it isn't an anomaly. It's just what that combination produces. You get a gargantuan storm running at nearly the maximum the physics will permit, walking west across open water toward a very small island. Which brings us to Rota. Rota is 33 square miles. That's the first thing to hold on to, because everything about what happened there follows from the size of it. 33 square miles is small. It's smaller than a lot of cities. You could walk across it. About 2,000 people live there, give or take, and it sits roughly 60 miles northeast of Guam in the Commonwealth of the Northern Mariana Islands, which is a US Commonwealth in the Western Pacific, thousands of miles from anywhere most people would consider the United States. It's the sort of place that appears in the news roughly never. It's quiet, it's green, it's got a limestone plateau and cliffs and a small airport and a seaport and not a great deal else. If you've heard of the Northern Marianas at all, it's probably because of Saipan or Tinian, which are bigger and busier and have more history attached. Rota is the one in between, the one that mostly gets left alone. On the morning of the 6th of July, the eye of Bavi passed directly over it. Not near it. Over it. The centre of the Typhoon tracked within about 2 miles of the island's northern coast, which at the scale of these things is a bullseye, and the island sat inside the eye wall for more than an hour inside the wall. Not inside the storm, inside the ring of thunderstorms where the strongest winds live, with the mesovortices and the scalloped edge and everything else in it. The National Weather Service office in Tian, Guam, did something rare in the hours beforehand. They issued an extreme wind warning. That's a specific product, and it's not one they reach for often. It exists for the arrival of the eye wall of a Category 5 storm, and its whole purpose is to say, in the most direct language the format allows, that the next hour is a survival situation rather than a weather event. Their guidance told people to treat the incoming winds as if a tornado were approaching, and move immediately to an interior room. The warning said in capitals that this was an extremely dangerous and life-threatening situation. Elsewhere they were plainer still. Venturing outside could result in death from flying projectiles, and unreinforced structures would be destroyed. That's not scaremongering. That's a forecast office with a small window and a very small island and no more polite way to put it. The NWS had warned beforehand that a direct hit would render most of Rota uninhabitable for weeks, perhaps longer. Here are the numbers from the moment it crossed. The Joint Typhoon Warning Center assessed 1-minute sustained winds of 285 km per hour, 180 miles per hour, with a central pressure of 901 hectopascals, gusts as high as 215 miles per hour. The Japan Meteorological Agency, using its own conventions, had it at 205 km per hour, with a pressure of 910. I'll come back to why those two numbers look so different, because there's a good and slightly boring reason, and it's worth a proper explanation rather than a footnote. And this is the bit that goes in the record book. According to the National Weather Service office in Guam and the Joint Typhoon Warning Center, that made Bavi the strongest tropical cyclone on record to strike United States territory. Not the strongest this year, not the strongest this decade, on record. It surpassed U2, which hit Tinian and Saipan in October 2018, and which had held that distinction for 8 years, and which had itself been described at the time as a historically significant event that was probably the strongest ever to hit the US and its territories. There's a second record sitting next to that one, and I think it's the more evocative of the two. Bavi's eye passing directly over Rota was only the 6th recorded instance of a Category 5 cyclone's eye reaching US soil. 6. In the entire record. That's how uncommon it is for the actual middle of one of these things to arrive over somewhere with a postcode. The Doppler radar at the Weather Service office in Tian showed Rota sitting inside the eye, right up until conditions knocked the radar offline. So, what did that actually do to the place? I want to hand this bit over to the island's mayor Aubrey Hocog, because she said it better and more plainly than any summary of mine would. Speaking to Stars and Stripes by phone the following Tuesday, she said the island had been damaged in every aspect. Then she listed it out. The public facilities, the government, the assets, the private residences, and then even the ports of entry, the airport and the seaport, had all taken damage. 2,000 people, no power, no running water. By that Tuesday afternoon, they'd tapped into a reservoir to get water flowing at all. The mayor's estimate was that at least half of the island's structures were damaged or destroyed, and that it might take months to fully restore power. And the ports being damaged is the detail that turns a bad situation into a slow one, which is the specific curse of small islands. Relief doesn't just arrive. The logistics of the Marianas mean that cargo vessels typically stop at Guam or Saipan first, and work outward to the smaller islands from there. So the bigger ports had to reopen before anything meaningful could reach Rota at all. The US Coast Guard spent days on the water and in the air across the chain-clearing navigation hazards and assessing damage, methodically, as one of their people put it, so they could reopen the ports properly the first time rather than quickly and wrongly. That's the thing about an island. There's no driving in from the next county over. Guam, 60 miles southwest, came off considerably better, and it's worth saying that clearly because it's the good news in this section, and it deserves its own space. Guam took the storm on its flank rather than through its middle. The governor Lou Leon Guerrero posted that most buildings had survived unscathed, and that roads were mostly clear by the Tuesday morning. Which, given what had just gone past, is remarkable, but better isn't fine. More than 2/3 of the island was still without power on the Wednesday morning. Of Guam's 120 water wells, 68 were online by Tuesday afternoon, and 74 by Wednesday. Around 10 major roads were impassable at the peak, blocked by flooding, fallen trees, downed utility lines and rock slides. Debris washed up across the beaches and onto the roads. There are photographs of a sand-covered Marine Corps drive and a traffic light hanging sideways over a junction in Hagåtña, which is the sort of image that tells you more than a wind speed does. Guam set a new daily rainfall record at its airport, 12.64 inches, top wind gust of 111 miles per hour, and an identical 111 recorded on Saipan. And Bavi produced Guam's first documented tornado. I love that detail, genuinely. The island has been getting hammered by typhoons for as long as anyone's been keeping track. It sits in what people actually call Typhoon Alley. And in all that time, with all those storms, nobody had ever documented a tornado there. This one did. Now here's the context that makes the whole Mariana story land differently, and it's the part I'd want people to remember. This was the second super typhoon to hit these islands in 3 months. In April, Super Typhoon Sinlaku made landfall on Tinian. It was the strongest storm anywhere in the Northern Hemisphere to form in April since Surigay in 2021. It killed 17 people across Micronesia and the Marianas, it knocked out power to tens of thousands, and it caused something like $1.5 billion in damage. People were still repairing roofs from Sinlaku when Bavi's forecast track started pointing at them. Across the 4 islands after Bavi, early estimates put at least 3,300 homes as suffering major damage or destruction. More than 280 Red Cross disaster workers went in, nearly 100 FEMA officials on the ground, twice in 3 months. 2 of the most powerful storms on Earth this year, both aimed at the same handful of small islands where about 200,000 people live in total. There is a version of this section that goes heavy on the drama, and I don't want to write it, because the actual story here isn't drama. Nobody died on Guam or the Northern Marianas. Not one person, through the strongest storm ever recorded to hit American soil, with an eye that went straight over a populated island. That's not luck. That's building codes and reinforced concrete and a culture that's had this happen enough times to know exactly what to do, and a weather service that used its most serious warning at the right moment, and people who listened to it. The islands got wrecked. The people came through. I'd take that trade every single time. There's a particular kind of week you have when a typhoon doesn't hit you. It's not relief exactly. It's this odd suspended thing where the storm is out there, hundreds of miles offshore, never going to come any closer, and the sky above you is still doing something terrible. The forecast says it's missing you, the rain says otherwise, and the rain wins because the rain is what's actually falling on your house. That was the Philippines, in the second week of July. Bavi never made landfall there. It crossed into the Philippine area of responsibility in the early hours of the 8th, picked up the name in day, and tracked west and then west-northwest across the Philippine Sea without ever coming ashore. On paper, that's a miss. On paper, the northern Philippines got lucky, because a Category 4 or 5 storm walking into Luzon is one of the genuinely nightmarish scenarios in this part of the world, and it did not happen. 18 people died anyway, none of them from the typhoon directly, every single one from landslides. And the mechanism is worth understanding properly because it's one of the least intuitive things about how storms actually kill people in this region. And it's not the wind and it's not the surge, it's the monsoon. The Philippines has a southwest monsoon, the Habagat, which runs through the middle of the year and brings moist air up from the southwest across the archipelago. It's a normal seasonal feature. It rains, everyone knows it rains. Life continues. What a large typhoon offshore does is act as an enormous vacuum. It's got an inflow, remember? All that air rushing inward toward the low pressure at its centre, and if the storm is sitting to the east of the Philippines, then that inflow is reaching across the islands and yanking the monsoon flow harder than it would otherwise go. The Habagat gets accelerated. More moisture, faster, dumping over the same slopes for longer. The storm doesn't have to touch you, it just has to sit nearby and pull. And this is why the deaths were landslides rather than anything else. Days of amplified monsoon rain onto steep saturated ground, and eventually the ground gives up. It's slow, it's not dramatic in the way a storm surge is dramatic, and it happens in places where the hillside above someone's house has been perfectly stable for decades right up until the moment it isn't. 12 more still missing as of that Sunday. More than 562,000 people across the archipelago affected, according to the country's Civil Defence Office. Every one of those from a storm that stayed offshore. Storms don't kill people in proportion to how strong they are. They kill people in proportion to what they find. Terrain, building stock, where people happen to live. Which particular mechanism is in play that week, anyway. Bavi kept walking west, and by the time it was clearing the Philippine Sea it was starting to lose the plot a little. Still a powerful typhoon. Still enormous. That gargantuan wind field from earlier was still doing its thing, spreading damaging winds across a width the peak intensity number never captures. But it was moving into an environment with more sheer and gradually cooler water, and it was, in the technical sense, coming off the boil. Next in the way, Taiwan. And Taiwan again, technically got missed. Bavi passed north of the island on the Saturday rather than crossing it, which given the mountains down the spine of Taiwan is the difference between a difficult weekend and a genuinely serious event. More than 100 weather-related injuries, widespread transport disruption, waves breaking over the coast at Yilan and Keelung big enough that people were photographing them, which is a phrase I always find slightly alarming, because the storm didn't hit and people were still standing on the coastline watching water do that. There's footage of it. Enormous grey walls of sea coming in at a right angle to a concrete promenade with a person in a raincoat standing there looking at it. And I understand the impulse. I do. I would absolutely be the idiot in the raincoat. But the ocean around a typhoon of this size is dangerous from a very long way off. The waves radiate outward. The storm's centre can be hundreds of miles away, and the sea at your feet is still being driven by it. Then Japan's southwestern islands, the Ryukyus, the long chain that stretches southwest from the main islands toward Taiwan. The storm passed about 300 miles southwest of Kadena Air Base on Okinawa as a Category 3 equivalent. Trees down, tens of thousands without power across the remote southwestern islands. Some injuries, real disruption, no catastrophe. 4 countries, 4 completely different weeks, 1 storm, and the wind speed explains almost none of the difference between them. What I keep coming back to on this stretch of Bavi's life is how much of the damage came from its size rather than its strength. Because after that eyewall replacement cycle, it was, physically, a very large object. Its rain bands eventually stretched something like 1,000 kilometres from one end to the other, roughly the length of France, which is a comparison I didn't come up with, but which I'm keeping because it does the job instantly. A storm that big doesn't need to hit you. It doesn't need to come within 200 miles of you. It just needs to be in your general neighbourhood and pointed vaguely your way, and its outer edges will find you. That's the thing that the headline number can't tell you. Everyone quotes the peak wind because the peak wind is the exciting bit and it's a single figure and it fits in a chiron. But the peak wind describes a ring maybe 40 kilometers across in the middle of a system that's 1,000 kilometers wide. If you want to know what a storm is going to do to a region rather than to a point, the size matters more. And there's one more thing about this leg of the journey that I think gets lost. Bavi was, at this point, moving toward one of the most densely populated coastlines on the planet. It had already broken a record on a tiny island of 2,000 people. It had already killed people in a country it never touched. And it was still, even weakening, an enormous system full of an absolutely staggering quantity of water aimed at a place where a lot of people live. So let's talk a bit about what China did about it, because the interesting part of that leg isn't meteorological at all. Roughly 2.8 million people were moved out of the way. That's the number. It's a logistics figure rather than a weather one, and I think it's the single most consequential thing that happened in this entire storm's life, and it almost never leads the coverage because there's no satellite photograph of it. Let me lay out the storm bit first, and then get to the interesting part. Bavi made landfall in China at about 20 past 11 on the night of Saturday the 11th of July at Yuhuan, a coastal city administered by Taiju in Zhejiang province. 10-minute maximum sustained winds of 144 kilometers per hour, which is about 90 miles per hour. It then made a second landfall at Yueqing near Wenzhou before pushing inland. By Sunday it had been downgraded to a severe tropical storm. By the afternoon of the 12th it had moved into eastern Anhui province, and from there it was forecast to drift on toward the Yellow Sea and come apart. So the storm that arrived in China was not the storm that hit Rota. Not remotely. It had spent days over cooler water and stronger shear, and it turned up as roughly a Category 1 equivalent, which for a coastline as Typhoon experienced as Zhejiang's is a serious weather event rather than a historic one. But it was still, as I said, 1,000 kilometers of rain bands, and the warning that went out wasn't really about the wind. China's National Meteorological Center issued the country's first red rainstorm warning of 2026. Red is the top of a 4-level scale. It went out for eastern Zhejiang and northeastern Fujian, alongside an orange typhoon warning, which is the second highest tier on that scale. The concern was water, an enormous, slow-moving, saturated system pushing inland over terrain that had already had a rough month. And it had. This is the context that makes the response make sense. Bavi was the second typhoon to hit China in just over a week. Maysak had come ashore in the south on the 3rd, and extreme weather across southern and central China in the preceding days had already killed at least 39 people, overflowed dozens of rivers, and burst a reservoir. Torrential rain further north had prompted the evacuation of more than 100,000 people from their homes around Beijing, with water discharge from the Miyun Reservoir being ramped up to make room for whatever came next. So Bavi wasn't arriving into a dry, rested landscape with plenty of capacity. It was arriving on top of a country that was already soaked and already dealing with the consequences. Right? The evacuation. More than 2.2 million people moved in Zhejiang province alone, over 100,000 in Fujian, where they also deployed more than 17,000 emergency rescue personnel ahead of time. Around 34,000 relocated in Shanghai, with some figures putting the Shanghai number considerably higher as the outer rain bands closed in. Thousands more in Ningde, national total roughly 2.8 million. The central government released about 40 million yuan, call it $5.9 million, in disaster relief funds before the storm arrived rather than after. Schools closed, workplaces closed, tourist attractions closed, outdoor activities suspended across the affected areas, more than 400 flights cancelled. There's CCTV footage of people reinforcing metal shop shutters with wooden planks and taping up windows, which is the same thing people do everywhere, in every country in front of every storm, and which I find quietly moving every time I see it. Same tape, same planks, same everything, and here's the number that the whole section is built around. 0 confirmed mainland deaths. A typhoon with a rainfield the width of France coming ashore twice, on top of a region that had already had a reservoir burst, in a country where 39 people had died from the weather the week before, and the confirmed death toll on the Chinese mainland from Bavi itself was 0. I want to be careful here, and I want to say plainly what I do and don't know. That's the figure as reported in the days immediately after landfall, and these numbers can move. Flood tolls in particular have a habit of climbing for weeks afterwards as people are found and as remote areas get reached. I'm not going to stand here and promise you it stayed at 0 forever. What I can tell you is that in the immediate aftermath of a very large typhoon making landfall on a heavily populated coast, there were no confirmed deaths, and that is not a normal outcome. And the reason isn't physics. That's my whole point. Nothing about the atmosphere made this outcome. The storm didn't go easy on anyone. It was buses, it was shelters, it was somebody in an office in Hangzhou making a call about which districts to clear and when. Days out, on a forecast that could have been wrong, it was 2.2 million individual people being told to leave their homes and largely leaving them. That's the bit I keep chewing on. We spend all this time, and I've spent most of this video doing it, on ocean heat content and eyewall replacement cycles and maximum potential intensity, and all of it is genuinely fascinating, and none of it saved a single person in Zhejiang. What saved people in Zhejiang was administration. Boring, unglamorous, deeply unphotogenic administration. Nobody makes a documentary about the coach that took 400 people inland on Friday afternoon. There's a comparison sitting there if you want it. Rota. 2,000 people, a direct hit at the maximum strength the ocean could produce, and nobody died. Zhejiang. Millions of people, a much weaker storm, and nobody died. The Philippines. No landfall whatsoever, and 18 people did. The Marianas came through on building codes and institutional memory. Eastern China came through on the buses, and the Philippines lost people to a hillside coming down in the rain, in places where evacuating is complicated and where the hazard doesn't announce itself with an eyewall on radar. That's not a criticism of anybody. Landslide risk is genuinely one of the hardest things in this whole field to warn for, precisely because it's not the storm. It's the ground, days later, somewhere the storm never went. There's one last thing about the Chinese landfall I want to mention, because it's such a strange little coda. By the time Bavi came ashore at Yuhuan, it was no longer the strongest cyclone ever to strike US territory. It was no longer a gargantuan Category 5 running near its theoretical ceiling. It was a 90-mile-an-hour storm bringing a lot of rain to a coast that has seen a great deal of rain. The record was already set. It was set 5 days earlier and 6,000 kilometers away, over an island most of the world had never heard of. And by the time Bavi got to the place where the most people lived, it was, meteorologically speaking, a shadow of the thing that had made it famous. Storms don't peak where it's convenient. They peak where the ocean tells them to. Why did two agencies looking at the same storm on the same day give you 285 kilometers per hour and 205 kilometers per hour? Straightforward answer, and it's not exciting, and I'm going to give it to you immediately rather than dangle it. They're measuring different things, and they always have been. The Joint Typhoon Warning Center uses 1 minute sustained winds. That means you take the strongest wind the storm can sustain averaged over a single minute. The Japan Meteorological Agency uses 10-minute sustained winds. Same wind, averaged over 10 times as long. And because wind gusts and lulls, a 10-minute average will always come out lower than a 1-minute average of the same storm. Always. It's not a disagreement, it's arithmetic. Stretch the averaging window, and you smooth out the peaks, and the number goes down. The rough conversion people use is around 12%, though it's not a clean constant. Run 285 through that, and you land somewhere close to 250. The JMA had 205, which is lower still, because they were also assessing the storm slightly differently in other respects. But the point is that most of that yawning gap between 285 and 205 isn't two organisations arguing. It's two clocks. That's it. That's the whole scandal. I labour this because every single time a big storm happens, someone notices that the American number and the Japanese number don't match, and concludes that somebody's hiding something. And I get it. Genuinely I do. Because if you don't know about the averaging conventions, then two authorities publishing two different numbers for the same object looks exactly like a cover-up would look. But think about what a cover-up would actually require here. You'd need the JTWC, which is American and military, and the JMA, which is Japanese and civilian, and Pagasa in the Philippines, and China's National Meteorological Center, and Taiwan's Central Weather Administration. All of them, simultaneously, coordinating a lie across national boundaries between organizations that answer to entirely different governments and have absolutely no incentive to protect each other's reputations, and every one of them publishing their fake numbers in real time on public websites, where anyone can compare them. Remember the three names from earlier? Same principle. The multiplicity isn't obfuscation. It's the fingerprint of several independent bodies, all watching the same thing in the open, and each using their own filing cabinet. If they were colluding, you'd expect the numbers to match. Right. Now the part that's actually interesting, which is that there's a real uncertainty underneath all this, and it's much more interesting than the fake one. We are genuinely quite bad at knowing how strong a storm is. Not where it is. Where it is we're excellent at. Track forecasting has improved enormously over the past few decades, and it's one of the quiet triumphs of the field. Forecasters can now often tell you where a storm centre will be days in advance, and be close enough that emergency planning actually works off it. The reason track forecasting got good is that a storm's path is governed by big things. It's steered by the large-scale flow of the atmosphere around it, vast ridges of high pressure, the broad rivers of air that move across whole hemispheres. Those features are enormous, they're relatively slow, and they're exactly the sort of thing a computer model can capture, because a model works on a grid, and big features fit comfortably inside a grid. Intensity is governed by small things. How strong a storm gets is decided in its core, in the eye wall, in the precise interaction between the storm and the specific patch of ocean directly beneath it, in whether an eye wall replacement cycle kicks off on Tuesday or Thursday, in the mesovortices, in the exact degree to which a bit of dry air gets pulled into the circulation at the wrong moment. All of those processes happen on scales far smaller than the grid. They're difficult to observe in detail, and they're even harder to simulate. So the situation you end up in is genuinely strange when you say it out loud. We can often tell you with real confidence where a typhoon will be on Thursday, while struggling to tell you how strong it'll be when it gets there. We've largely solved the where. The how strong is still stubbornly open, and rapid intensification is the very worst case of that problem. It's the place where our predictive ability is weakest at exactly the moment the stakes are highest. Forecasters could see on the 2nd of July that Bavi was in an environment favourable for it. They said so. The JTWC assessed the environment as highly favourable for continued rapid intensification, and they were right, and their forecast called for a super typhoon. They flagged it properly and early. But the specifics, how fast, how far, when exactly, depend on those small core details nobody can fully see. So what actually happened is that Bavi's intensification, when it came, partly outran the early projections. The storm climbed faster than the initial numbers suggested it would. That's not a failure. I want to be really clear about that, because the forecast was wrong is a lazy thing to say about people who got the hard part right. They flagged the risk, they named the mechanism, they updated as fast as the data allowed. What it reflects is that this is a genuinely brutally difficult problem, and that even with satellites watching every patch of ocean and models running on machines of staggering capability, the atmosphere can still assemble something faster than we can describe it. Which brings me to how they get the intensity number at all, because this surprises people. There's no instrument in there. Bavi spent its entire intensification over open water hundreds of miles from anything. Nobody flies routine reconnaissance aircraft into Western Pacific typhoons the way they do into Atlantic hurricanes. The distances are enormous and the program doesn't exist in the same form. So the intensity of a storm out there is largely estimated from satellite imagery, using techniques that read the storm's appearance and infer its strength from it. The main one is called the Dvorak technique, and it's over 50 years old, and it's one of the great pieces of practical science in the field. The idea is that a storm's appearance from above encodes its strength in a fairly reliable way. How well defined is the eye? How cold are the cloud tops? How symmetrical is the central dense overcast? How tightly is it all wrapped? You score these features against a set of patterns, you arrive at a number, a T-number, and the T-number maps onto a wind speed. There's now an automated version, the advanced Dvorak technique, which does this by algorithm rather than by a human squinting at a screen. For Bavi at one point it put the estimated peak winds near 135 knots, at a Dvorak intensity of 6.8, with a central pressure around 916 millibars. So when you see 180 miles per hour, what you're actually looking at is an inference. A very good, very well calibrated, decades refined inference drawn from a picture. Not a reading off a dial. And that's the honest uncertainty. It's real. Different agencies applying different conventions and different weightings to the same imagery genuinely will arrive at somewhat different numbers, and they'll tell you so, because it's discussed openly in the literature and in the products themselves, which is the opposite of a cover-up. The uncertainty is published. It's built into the science. The thing people think is being hidden is written down in the manual. What none of them disagreed about, incidentally, is the part that mattered. Every agency watching Bavi agreed it underwent explosive rapid intensification and became an exceptionally powerful storm. The argument, such as it was, concerned the precise size of the thing, not whether the thing was there. And I'd rather have it this way. I'd rather have 4 organisations publishing 4 slightly different honest estimates, with the uncertainty stated, than one organisation publishing a single confident number that nobody can check. An honest number with error bars is worth more than a clean one without them. The last thought I'll leave on this. There's a quiet irony in the whole business that I find genuinely humbling rather than depressing. We live in an age of extraordinary observational power. We have satellites over every patch of ocean, taking imagery constantly, in visible light and infrared and microwave. We have radar. We have models running on machines that would have looked like magic to a forecaster in the 70s. And a patch of warm water and a favourable sky can still, in a single day, assemble something more powerful than anything we've ever built, and less predictable than we'd like to admit. We're not the masters of this system. We're observers of it. Increasingly good observers, but observers, watching something much larger than us, trying imperfectly to understand it well enough to stay out of the way. There's something quite healthy in that, I think. Now, let's talk a little about the stretch of ocean this all happened to land on, because there's a reason it keeps being the Marianas. People who work in this field call it Typhoon Alley. It's not an official designation, it's just what it is. A corridor across the Western Pacific where intense tropical systems get tracked as they move west, and Guam and the Northern Marianas sit more or less in the middle of it. Not near it, in it. The geography is unkind in a very specific way. Storms in this basin tend to form to the east and travel west. Guam is about 550 miles east of the Philippines, and something like 3,800 miles west of Hawaii, which means it's sitting out in the middle of the run-up, right at the point where a storm has had enough open water to organise but hasn't yet had enough time or latitude to weaken. Islands further west get storms that have already been going a while. Islands further east get systems that haven't got going yet. The Marianas get them in their prime, and the history reads like it. Karen, Paca, Pongsona, those are names that mean something in Guam in a way they mean nothing anywhere else. Mawar in May 2023 was a Category 4 that pushed up to 14 feet of storm surge and dropped 1 to 2 feet of rain on the island. Yutu in October 2018 put 175 mile-per-hour winds across Saipan and Tinian, stripped vegetation off parts of the islands, damaged Saipan International Airport, injured over 100 people and killed 2. There's an infrared satellite image from that one showing the island of Tinian completely engulfed by the eye, which is one of the more sobering photographs I've seen. An entire island sitting inside the calm bit. So this is not a place that gets surprised. And that's the whole reason the death toll from Bavi across those islands was what it was, which is to say nothing. The buildings are the first thing. A lot of construction across Guam and the Marianas is reinforced concrete, and it's reinforced concrete specifically because reinforced concrete stands up to wind that would peel a timber-framed house apart like a magazine. That's not an aesthetic choice, and it's not a coincidence. That's a civilization that has been handed the same problem enough times to have arrived at the same answer. The systems are the second thing. When Bavi's track started pointing at the islands, 3 major military installations on Guam, Anderson Air Force Base, Naval Base Guam and Marine Corps Base Camp Blaz, went to their highest tropical cyclone readiness conditions. The Coast Guard closed the ports at Guam, Saipan, Tinian and Rota, pulled its small boats out of the water and sent its cutters away to ride the storm out somewhere else, which is a genuinely clever bit of thinking. A cutter is safer in open water than tied to a pier during a Category 5. Guam opened 5 emergency shelters on the Saturday. None of that got improvised. All of it exists as a plan that gets pulled off a shelf. The third thing is the least tangible and probably the most important, which is that everybody there knows. There's a cultural memory of these storms that runs through generations. People know what to do, because their parents knew what to do, and because a lot of them did it 3 months earlier for Sinlaku, which is, incidentally, the part of this that I think doesn't get enough attention. Sinlaku hit in April, Bavi hit in July. That's 12 weeks apart. People who had spent that spring putting roofs back on and getting power restored and hauling debris off their properties then had to do the entire thing again, from the top, while still not finished with the first one. There's a line from Brad Kieserman at the Red Cross about that, about the reality that should stay with all of us, and I've thought about it a fair bit. Because the news covers a disaster for about 4 days and then leaves, and the actual experience of a disaster is measured in seasons. The Red Cross had more than 280 disaster workers on the ground after Bavi. nearly 100 FEMA officials, and they weren't arriving at a clean slate. They were arriving at an archipelago that was already mid-recovery from the last one. Rota's mayor said it might take months to fully restore power. That's not months of drama, that's months of Tuesdays. And Sinlaku had form for that too. It didn't just knock things down and leave, it hung around. There's a line from one of the Guam forecasters after Bavi that I thought was quietly revealing. Conditions were going to improve, he said, and that was great news, because it wasn't going to linger the way Sinlaku had in April. That's the mark a storm leaves on a place. 3 months later, the professionals are still using it as the yardstick for what a bad one feels like. Sinlaku knocked out power to something like 43,000 people across the Marianas. It ripped roofs off, and it produced one of the more awful details of the whole year out there, which is that a cargo vessel overturned during the storm, the sort of maritime consequence that doesn't make a headline anywhere outside the region, and that changes everything for the people involved. So when Bavi's forecast track started swinging toward the same islands 12 weeks later, it wasn't arriving somewhere abstract. It was arriving at an archipelago where a lot of people were still living under a tarpaulin from the last one, where the debris piles hadn't all gone, where the insurance claims were still open. Here's a small thing that says a lot about how these islands work. When the ports were shut, relief couldn't reach Rota until the larger ports reopened first, because the whole supply chain routes through Guam or Saipan, and then outward. So the Coast Guard's priority wasn't Rota directly, it was reopening the hubs, deliberately and carefully, so everything downstream could start moving. One of their people described spending days on the water and in the air, methodically clearing waterways so they could reopen the ports the right way the first time. There's a version of that sentence that sounds like bureaucratic hedging, and there's a version that's just correct, and I think this is the second one. Reopening a port badly and having to close it again is worse than taking an extra day. The other side of it, and I want to say this plainly because I don't want the preparedness point to slide into complacency, is that being prepared is not the same as being safe. Rota was as prepared as anywhere on Earth. Rota had reinforced concrete and a warning system and a population that had done this before, and half the structures on the island were still damaged or destroyed. The airport and seaport still took damage. 2,000 people still lost power and water at once. Preparedness didn't stop the storm doing what it did to the island. It stopped the storm doing it to the people. That's a real and enormous distinction, and it's the reason those islands can take a hit that would produce a mass casualty event almost anywhere else, and come out with a damage report instead of a death toll. The buildings are replaceable. That's the deal. That's the whole deal, and they've known it there for a very long time. Here's a detail I didn't expect when I started reading around this. Bavi was the third Category 5 storm on Earth in 2026. Not the third in the Pacific, the third on the planet. The first was Tropical Cyclone Horatio in the southern Indian Ocean, back in February. The second was Sinlaku in April, the one that hit Tinian, the one that was the strongest storm anywhere in the Northern Hemisphere to form in April since Surigay in 2021, and which at the time was the strongest tropical cyclone worldwide of the year. Then Bavi in July. 3 top-of-the-scale storms in 7 months across the whole world, and 2 of them hit the same tiny island chain. I don't have a tidy conclusion to hang on that. It's just a fact that sits there being slightly absurd. Of all the coastline on Earth, of all the places a Category 5 can happen to arrive, 2 of the 3 went to a group of islands with a combined population of about 200,000. Some years are just like that. That's not a cop-out, that's genuinely how it works. Storms don't distribute themselves fairly, they go where the physics sends them, and sometimes the physics sends 2 of them to the same doorstep. But there is something going on in the background of 2026 that's worth talking about properly, and it's the thing that explains why the ocean under Bavi was in the state it was in. El Niño. Now, I want to do this carefully because this is exactly the sort of topic where it's easy to slide into either this proves nothing or this proves everything, and both of those are wrong, and I'd rather just tell you what's actually measured. The tropical Pacific swings between warm and cool phases on a cycle. The warm phase is El Niño, the cool phase is La Niña, and scientists track where we are with an index, a single number telling you how far above or below normal the sea surface temperatures are running in a particular monitored region of the central Pacific, called Niño 3.4. Here's what that number did in 2026. Over March to May, the index averaged plus 0.48. That's in the neutral range, technically, leaning warm, not yet El Niño. In May alone, it hit plus 0.94. And by the weekly reading centred on the 17th of June, it had climbed to plus 1.7. That's a fast climb. That's the tropical Pacific going from arguably nothing much to a solidly established El Niño inside a few months. NOAA's National Weather Service announced that El Niño had developed and issued an El Niño advisory. As of the most recent Climate Prediction Centre discussion, the synopsis is that El Niño continues and will strengthen through the end of the year, with a 97% chance it persists through early spring 2027. Some models have it going very strong, the kind of territory the press starts calling a super El Niño, which requires sustained anomalies of plus 2.0 or higher. And underneath the surface there's a genuinely striking signal. Between roughly 150 west and 80 west, at depths of 50 to 150 metres, temperatures have risen substantially, with anomalies locally reaching up to 6 degrees. That's a very large subsurface heat reservoir. For context, and this is the comparison that made me sit up, the ocean heat content anomalies through the upper 300 metres across that stretch are running at almost double what they were at the same point in mid-June 2023, during the development of the El Niño that year. So that's the state of the water, that's the basin Bavi was born into. Now, does El Niño explain Bavi? Here's the careful version, and it comes from Jeff Masters, who's a meteorologist who used to fly into these things for a living and who's forgotten more about them than I'll ever know. His point is that Bavi is the type of storm you might expect when a strong El Niño is building, which is currently the case. And the mechanism he points to is genuinely interesting because it's not the obvious one. The obvious guess would be warm water, therefore stronger storms, and that's too crude. The actual argument is about geography. In El Niño years, Western Pacific typhoons tend to form further east than usual. The warm water shifts, and the zone where storms get their start shifts with it. And a storm that forms further east has more room. That's it. That's the whole thing. More open ocean between where it's born and where it hits anything. More days of unobstructed westward walking over warm water with nothing in the way. More time to find its ceiling, which is exactly what we talked about right at the start, with the empty stretch between Kwajalein and the Marianas. A clean run with nothing to trip over. El Niño makes that run longer. I like that explanation a lot, and I like it specifically because it's not a hand wave. It's a testable, mechanical claim about where storms get born and how much road they get. It's the kind of thing that can be checked against the record rather than asserted. But, and this is where I have to be honest with you, because honesty is more or less the point of doing this at all, one storm doesn't prove any of it. Bavi is a single data point, a single, extremely well-observed, genuinely remarkable data point. It fits the pattern that the El Niño framing would predict. It formed east, it had a long run, it found deep warm water, it went to the top of the scale. Every feature of it sits where you'd expect a data point to sit if the framing is right. And a point that lands on a line is not the same thing as the line being real. Anyone who tells you a single storm proves a trend is selling you something, and it doesn't matter which direction they're selling in. The person who says this storm proves the climate is collapsing, and the person who says this storm proves nothing is happening, are making the identical error from opposite ends. They're both taking one event and loading it with a certainty it can't carry. What a single storm can do is be a reading, a measurement of the state of a basin at a moment in time. Bavi is telling us that in early July 2026, the Western Pacific held enough deep heat, in the right place, with the right winds above it, to build a storm that ran almost to its theoretical maximum. That's a real piece of information, and it doesn't require any extrapolation to be interesting. The rest, whether this is a rare alignment or the early legible edge of something shifting, is written in the sequence, not the point. And the sequence takes years to read. So I'm not going to tell you what August holds. I don't know. Nobody does, and the ones who claim to are guessing with more confidence than the evidence supports. What I'll say instead is the boring true thing. The water is warm, the El Niño is strengthening, and the season isn't over. That's not a prediction. That's just the state of the board. And the honest position, the one that doesn't give you a villain or a verdict, is to file the point, notice where it landed, and keep watching for the next one. which is less satisfying than certainty in either direction and considerably more useful. I've said watching about 9 times now, so let's talk about what that actually involved, because the way we looked at this storm is quietly one of my favourite parts of the whole thing. Most of the imagery you've seen of Bavi came from Himawari 9. That's a Japanese geostationary weather satellite, and geostationary means it sits about 36,000 kilometres up, directly over the equator, going around the Earth at exactly the speed the Earth turns. So from the ground it never appears to move, it just hangs there, permanently, staring at the same face of the planet, which means it never blinks. It takes an image of the whole disk of the Earth every 10 minutes, and of specific regions far more often than that, and it has done so continuously for years. Every satellite loop you've watched of a typhoon spinning, that hypnotic thing where the clouds wheel round and the eye opens like something breathing, is Himawari frames stitched together. The storm didn't move like that. The storm moved at about 15 miles an hour. We're just watching a week of it in 9 seconds. That's the workhorse. But the image from this storm that I keep going back to came from somewhere else entirely, and it's genuinely beautiful, and I want to describe it properly because it's worth describing. At 3:30 in the afternoon UTC on the 5th of July, 1:30 in the morning, local time, on the 6th, a satellite called NOAA 20 passed overhead and photographed Bavi's eye by moonlight. Not infrared. Not a false colour heat map. Actual visible light at night from the moon. The instrument that does this is called VIIRS, the Visible Infrared Imaging Radiometer Suite, and it has a mode called the day-night band, which is sensitive enough to image the Earth's surface using nothing but reflected moonlight, starlight and whatever else is going. It was built partly to see city lights and fishing fleets and gas flares. But if there's enough moon, it can photograph clouds at night the way your eye would see them if your eye were in orbit, and considerably better than it is. And what it caught was the western side of Bavi's eye wall lit up in moonlight, hours before the eye went over rotor, at its absolute peak. I've looked at that image more than is probably reasonable. There's something about it that infrared can't do. Infrared imagery is informative. It tells you cloud top temperatures. It tells you where the deep convection is. It's how the professionals actually assess these things. But it looks like a diagram. It looks like data. It's got that false colour palette where the coldest tops go purple and black, and the whole thing reads like a medical scan. The moonlight image doesn't look like data. It looks like a photograph of a thing, which it is. There's a hole in the cloud and the wall around it is picked out in soft grey light, and you're looking at the exact structure we spent 2 sections talking about. The eye, the wall, the symmetry, rendered the way it actually looked at 1:30 in the morning to nobody at all. Because that's the bit that gets me. Nobody saw it. There was no one down there. The eye of the most powerful storm ever recorded to hit US territory was sitting over empty black ocean in the middle of the night, lit by the moon doing that, and the only witness was a satellite in polar orbit going past at about 7 kilometers a second. 3 days later, on the 8th, its sibling NOAA 21 took another one as Bavi moved west over the Philippine Sea. Different satellite, same instrument family, and by then the National Weather Service had it at 250 kilometers per hour, 155 miles per hour, still an extremely powerful typhoon, still enormous, walking toward Taiwan. The polar orbiters like NOAA 20 and NOAA 21 work completely differently from Himawari. They go round pole to pole, low down, a few hundred kilometers up, and the Earth turns underneath them, so they don't hang over anything. They get one pass, one strip, and then they're gone and they'll be back in a few hours over a slightly different line. So you've got 2 entirely different philosophies of looking at the same object. One satellite that never moves and sees everything all the time at moderate detail. Others that sweep past occasionally and see a narrow strip in extraordinary detail. And then there's the third one, which is the one that does the actual work and which nobody ever shows you because it's ugly. Microwave imagery. The problem with everything I've described so far is that it only sees the top. Visible light, infrared, moonlight. All of it is looking at the lid. The high cloud spreads out over the storm like a duvet and hides the interesting bits underneath. So from above, a storm at its peak and a storm that's quietly falling apart inside can look fairly similar for hours. Microwave sensors see through it. Different wavelengths, and at those wavelengths the high cirrus is more or less transparent while the heavy rain underneath isn't. So you get to look at the plumbing, the rain bands, the eye wall itself structurally rather than the cloud sitting on top of it. On the 4th of July, microwave imagery of Bavi showed a strong inner core surrounded by a ring of weaker convection further out, which, if you've been paying attention, is exactly what we talked about a while back. That ring is the outer eye wall forming. That's the replacement cycle starting, visible in the plumbing, before the wind speed had done anything much to reflect it. The pictures are hideous. They're low resolution and false coloured, and they look like a weather map drawn by someone having a difficult time, and they're the ones that tell you what's actually going on. The picture forecasters work from is all of it together, plus the radar on Guam, right up until the wind took it out. There was also, I should say, a genuinely deep analysis of Bavi done by the people at SIMS in Wisconsin, the same group whose maximum potential intensity numbers came up earlier. They put out a piece going through products most people never see, and their framing for why they bothered has stuck with me. An extraordinary storm deserves an extraordinary analysis. That's a nice attitude to have about your job, and it's worth remembering when you look at any of these images that the whole apparatus exists for a reason that isn't beauty. Himawari isn't up there to make loops for weather channels. Viz isn't imaging eye walls by moonlight for the aesthetics. All of it exists so that somebody in a forecast office in Tian, Guam at 2 in the morning can look at a picture taken from 36,000 kilometers up and decide whether to issue the warning that tells 2,000 people on a small island to get into an interior room right now. That's the actual product. The image is just how it gets there. One more thing about Bavi that I don't want to leave out because it's the hazard that gets the least attention and it's arguably the one that does the most. On the 3rd of July, while the storm was still out east of the Marianas doing its explosive bit, significant wave heights of 12 meters were reported. That's 39 feet. And significant wave height doesn't mean the biggest wave. It's a specific term and it's a bit of a trap. It's roughly the average height of the highest third of the waves, which means that in a sea with a significant wave height of 12 meters, there are individual waves considerably larger than 12 meters, routinely, all the time. The occasional one will be half again as big. 39 feet is the typical big wave, in open ocean, hundreds of miles from anything. By the time Bavi reached the Marianas, the National Weather Service was warning of destructive waves reaching up to 35 feet. And waves aren't even the main event. Surge is. I should explain what storm surge actually is, because it gets used interchangeably with flooding, and it isn't the same thing at all. Two things push it. The first is the pressure. A typhoon's centre is a region of very low air pressure, and air pressure is literally weight. It's the atmosphere pressing down on the sea. Take the weight off, and the sea underneath rises slightly. Not dramatically. It's a bulge, a few tens of centimetres, following the eye around like a dent in reverse. The second is the wind, and the wind is the one that matters. A storm's winds don't just blow over the sea, they drag it. Hours of enormous wind pushing in the same direction piles water up ahead of the storm and shoves it toward whatever's in the way. And if what's in the way is a coastline, the water has nowhere left to go but up and inland. So it's not a wave, it's not a wall of water arriving like a tsunami, it's the sea level itself going up, arising and then not going back down for hours, with the waves riding on top of the new higher sea and breaking somewhere that used to be a car park. That's why it kills. Not because it's fast, but because it's high and it's heavy and it stays. And this is where the island problem bites, and it's the thing I said earlier about there being no driving in from the next county over. On a continent you can move people inland. The surge and the waves are a coastal hazard, and coasts have a hinterland. You get people 20 miles back from the water, and the ocean simply cannot reach them, no matter what it does. On an island, everywhere is the coast. Rota, remember, is tiny. There is no point on it that's far from the sea in any meaningful sense. Same for Tinian, same for Saipan, same for Guam. So when a storm generates a sea like that, the sea is a hazard for everyone simultaneously. You can't step back from it. You can only get behind something. And the waves outlive the storm. That's the other thing. Long after Bavi had pulled away west, the Coast Guard was still working across the Marianas clearing navigation hazards from waterways, because the sea had spent 2 days rearranging the coastline and putting things in it that shouldn't be there. Rough surf and localised flooding risks were expected to persist for days after the winds had eased. There are photographs from Guam of debris washed ashore at a park in Hagotnya, just piles of it, sitting on grass, well inland of where the water is supposed to stop. Somebody's going to have to move all that by hand, and the swell travels. That's what caught Taiwan, really. The storm passed to the north and never came ashore, and the ocean around the island still went mad because a system that size drives waves outward for hundreds of miles in every direction. The people standing on the promenade at Keeling watching grey walls come in were watching a storm that was nowhere near them. I think surge and waves get undercovered for a simple and slightly depressing reason, which is that wind is a number, and water isn't. Wind gives you a single figure. It's comparable across storms. It sits in a headline. Everybody understands it instantly. Water gives you what? It depends on the tide. It depends on the shape of the bay. It depends on the angle the storm comes in at, and the slope of the seabed offshore, and whether there's a reef, and whether the reef survived the last one. Two identical storms hitting two coastlines 100 miles apart will do completely different things with the sea. There's also the tide, which is the cruelest variable in the whole business. Surge doesn't arrive in isolation. It stacks on top of whatever the tide happens to be doing at that exact hour. The same storm hitting the same coast, 6 hours apart, produces two completely different outcomes. Arrive at low tide and a lot of the surge gets absorbed by the fact that the sea was low to begin with. Arrive at high tide and you're adding it to a sea that was already at its maximum, and the water goes further inland than anyone modelled, which means the difference between a difficult night and a catastrophe can come down to the moon. Not the storm, not the ocean heat, not the shear, none of the things I've spent 2 hours banging on about. The moon, and where it happens to be, and what that's doing to the water in that particular bay at the moment the wind arrives. I find that genuinely absurd and I love it. All that physics, all those satellites, and the last variable is a rock 250,000 miles away with a completely indifferent timetable. So it doesn't headline. And historically, across the world, storm surge has been the single deadliest element of tropical cyclones, because water is heavy and it's relentless, and it goes exactly where the low ground is, which is precisely where people build things. Wind breaks the roof, water takes the house. Anyway, that's the sea. It's the part of the storm that arrives before the storm and stays after it, and it's the part nobody puts on the graphic. So that's Bavi, 25th of June, a smudge of cloud near an atoll almost nobody could point to on a map. 11th of July, a rain band coming ashore in Zhejiang with 90 miles an hour left in it. Somewhere around the 14th, gone entirely, drifting out over the Yellow Sea as nothing much at all. 17 days, from nothing to the record books and back to nothing. And now it goes into a database. That's genuinely what happens. It becomes a track file. A list of positions and pressures and wind estimates 6 hourly, from birth to dissipation, sitting in an archive with every other storm anyone's ever measured. Some of those track files go back to the 19th century and are basically ship's logs and guesswork. Bavi's will be one of the most thoroughly documented in the whole collection. The name is the last loose end. Countries can ask for a name to be retired if a storm was bad enough, and the committee that maintains the list will take it off and someone will submit a replacement. Whether Bavi goes is not for me to guess. It's a decision made in a meeting, by people weighing damage and deaths, and how a name is going to land for the people who lived through it. If it stays on the list, it comes round again in a few years, and gets handed to some new disturbance sitting over warm water somewhere, which will probably do nothing at all. That's how it went for the 2021 after all. I've got a whole video I want to make about the 2026 season as it goes on, because there's a lot of water out there and the year isn't finished. That'll come when it comes. For now it's the middle of the night and I've been talking about a storm for 2 hours. The ocean's still warm, rotor's still fixing its roofs. Sleep well.